Hello, good afternoon, everybody.
Hi.
I'm Piotr Wojda. I'm chairing this session with my
Hello,
colleague.
Piotr. Can you hear me?
Yes, I can hear you.
Okay, very well. I will make, let's say, you as organizer. Okay, thank you. Thank you also to Patricia. Patricia, thank you. I now has arrived Piotr, so I don't need that you will stay more. But yeah.
Okay.
There was no chair at the moment, no. So I need at least one of the three chairs present.
Okay.
I was actually changing environments.
just one question. The room is not showing the board, so I'm kind of worried about it. It will open.
Sorry.
The room, the next room.
No, the room will open at 14:30. Okay, so we are just speakers.
Okay, so.
Okay.
Bye.
Okay, very well. Oh, Piotr, I leave the floor to you. You are the head, and you are allowed to stop any speakers for every reason. You are the king of this session, no? So.
Thank you. Thank you very much.
I recommend a good panel discussion. Remember, I would remember to everybody that you have the power to postpone the ending at 4:45. So a quarter of time more than if there are more questions. Don't know, but then close, Piotr, because we'll start another session. Okay.
Just to make sure, I'm looking for my co-chairs. So Dietmar and voters.
I don't see them. In case Patricia may help you, but
because I exchanged a couple of messages with them and they were
exactly. But in 2 minutes will arrive. Let's say people inside. Also,
and we will automatically go online, yeah? Automatically.
Yes, it will go online directly.
Okay.
Yes, absolutely.
Okay. No
See
problem.
you.
See you. So just to let you know, thank you very much to all the speakers that you are here with us. And in 1 minute and a half, we'll go automatically online. So then the room will open and then everybody can connect to the session. It's a sustainable management of contaminated sites. Actually, I work for the European Commission Joint Research Center. This is the center that is in charge of making the bridge between policy and science. And I deal with soil science and contaminated sites and some other issues. So I'm very glad that I'm here with you and I will be listening to all the presentations. I will make then online a brief introduction to the session and then let the first speaker and with the first subject, so selection of sustainable remediation strategies. Okay, Francisco, you are going to present. So then I go according to plan. And if you have maybe 15 seconds presentation for yourself, you can maybe introduce yourself just at the beginning of the session. So I'm controlling to see how more seconds do we have. Okay, probably we are entering online now. So the room should be opened. I'm looking at the list of participants, so it will be growing. So trying maybe one or 2 minutes just to speak, to wait for people to connect. I don't know if you've had the chance to participate in this morning session. It was a policy session that my colleagues from the European Commission and European Environmental Agency opened, talking about some policy considerations concerning the European Green Deal, then going to Zero Pollution Action Plan, and some considerations on soil in general. Still waiting, maybe a bit more. How many are we in this room? 12, okay. I would just double check online. Tech meters, just to be sure that everything is fine. So one more minute and I will invite Francisco. Okay, so maybe we can start, at least kick off. So welcome to this session. That's there is some change in the screen. Voters is connecting. Welcome to this session of sustainable management of contaminated sites. We are going to hear 7 presentations, and I think that in the current policy perspective, the theme of contaminated sites is getting more and more importance. We are speaking about some kind of trend. We, from the European side, through IONET network and the Environmental Agency, we have a lot of experience. We have launched a couple of questionnaires trying to see how much the soil is contaminated and how many contaminated sites we have, and in what management status they are. So to see if they are, first of all, recognized, localized, and then maybe characterized and even remediated. So this kind of statistics is very valid. It shows an image of the situation. So I'm very curious to hear all the presentations. I will ask now the first speaker, Francisco, who is going to present you the selection of sustainable remediation strategies based on high resolution investigation approach. So please, Francisco, the floor is yours.
Okay, thank you. Hello, everyone. Good morning, good afternoon, good evening. I'm just going to start sharing here. Can everyone see?
Yes,
Fine?
we see the presentation and we hear you well.
Perfect. So, as I said, my name is Francisco. I'm talking from Brazil. I'm going to be representing Finkler, an environmental consultancy company, and I'm going to be presenting the selection of sustainable remediation strategies based on a high-resolution investigation approach. First, I want to talk about the journey to sustainable remediation. At first, we realized that we have to manage our wastes, and our first approach was to simply discard them. And as we discarded them, we took this waste from one place to the other. And later on, we realized that this place that we put the waste was going to be contaminated. So we have to intensify our treatments. And then we started by digging, pump, burying, and although we would actually eliminate the contamination, we realized that the waste of the use of energy and the emissions of greenhouse gases were too much. So we have to develop sustainable methods. And by that, we mean applying more recycling, reuse, transforming, and biodegrading to the remediation. So how it is applied nowadays, we have ISO 18504 from 2017. We have SURF from UK, US, Australia, New Zealand, Nicole. But well, what all those guides and metrics and methodologies have in common? They all say that in order to achieve sustainable remediation, you must consider these three aspects: the economic, the environment, and the social one. Here's an example from SURF UK, where we have many parameters to be evaluated. If we take the first one, air emissions, we can apply quantitative metric, the CO2 emissions. In the first economic one, we can actually see the value, the money, so the direct economic costs. And those are two examples of quantitative metrics applied to the sustainability. But in general, what all the guides and the methodologies have is that they say that we should have a subjective and qualitative approach to the project. And that's because each project has its own characteristics, each site has its own perspectives, each country has its own legislations, each client has its own needs. So you're not able to apply a fixed rule to every project. So in each case, the people that are responsible for the project should select the metrics and the factors that are applicable to each case. Now I'm gonna analyze a study case. So speaking about the site, it is an active industry. It has a large area, a complex lithology, suffered many alterations during the last 50 years. Mostly of them were anthropic. And due to some previous environmental studies in the area, we know the sources of contamination, but they're not well delimited yet. Before our approach, there was an original proposal. They set about they used high resolution site characterization technologies. They used MIP and log and OIP. Here on the right, I have an example of the MIP log from this site. So the graph in the middle and the one in the left, it's from, there's an inert gas that goes deeper with the probe when it's going down in the soil. And then this inert gas can bring the VOC to the surface, where there is a gas chromatograph that analyzes it and then measure the current. On the graph on the right is an hydraulic profiling tool log, which is an estimative of the permeability of, the soil. With this data in mind, the proposal of this company was to do an excavation just in the unsaturated zone. And after that, for the saturated zone, apply dual phase extraction combined with R-sparging and dynamic groundwater recirculation, and finalize with monitored natural attenuation. The big picture here is that, as we can see in the HPT log, it's a really unpermeable soil. Therefore, their pilot testing for the installment of the dual phase extraction remediation system indicated that the effective porosity of the soil is only 0.9%. And therefore, a normal pump would only get around 4 liters per hour. And if you think that there's a huge amount of contamination absorbed in the soil, acting as a second source of contamination, the dual phase extraction won't be effective, because it's only going to measure the dissolved phase. Therefore, the remediation itself is not completely effective, and the removal of the contaminant doesn't really happen. Here is our approach to the problem. So we decided to intensify the high resolution technology investigation. Through that, we were able to better identify the center of the mass of the contamination. And by some estimatives, we realized that around 98% of the mass of contaminate were located in the center of the mass. And therefore, if we focus our excavation on these spots, we're gonna excavate less than if we only focus on the unsaturated zone. So by excavating both the unsaturated and saturated zone, but with the knowledge of the exactly location and how it is distributed, how this contamination distributed, we're gonna remove a higher amount of contamination, and by this way we're gonna end the second source of contamination. Our second stage is to promote a biostimulation with a soil mixing and chemical oxidation in order to deal with this with this 2% of contamination that is left. So since we don't have a second source of communication that is always feeding this rest of contamination, we're not going to increase the amount. We're always diminishing the amount of contaminant that we have in the soil. In addition, we're going to use a biopile in order to remediate the excavated soil. And after that, we're going to monitor the whole site with natural attenuation. Here we have an estimative of the CO2 emissions of this two different approach. So we have done an estimation that the mass in the saturated zone is around 5,000 kilos. And with pump and treat with the recirculation, operating 24 hours during 7 days a week, the original proposal said that they would take 2.5 years in order to solve the problem and remediate the site. But as we know, that only 0.9% is the effective porosity, and you only pump 4 liters per hour. The actual removable mass in this period is only 10 kilos. And if you consider that the main pump of the pump and treat system has 9 kilowatt, when you multiply this by 2.5 years, it's actually an emission of almost 140,000 kilos of CO2. On the other hand, our approach with the excavation of the second sources, we estimated that would take around 6 months. And if we put in account the amount of diesel that the excavator and the supporting vehicles would use, it would be an emission of around 5,000 kilos. But we are going to be removing almost the entire mass in saturated zone, around 5,000 kilos. So if we make a simple calculation, the CO2 emitted per kilo of mass removed in the first case is 14,000 kilos, while in our approach was only 1. When we bring this to the reality of the sustainable management and the approaches that the guides propose, we can easily sustain that it is not possible to manage if you're not completely sure of how your contamination is distributed, how your soil will determine the distribution and the movements of this mass. So the data must be all connected and interpreted and connected and interpreted in order to better evaluate the best approach. As this study case shows, the most intrusive methods might not be the ones with the biggest impact. And that is because if you consider the entire life cycle of the project, the effective of the remediation is way higher if you emit CO2, if in some cases you emit high quantity of CO2 in just a short period of time. Because if you take the long term, the estimation of 2.5 years, it's definitely not going to happen. It will be 15 years or maybe 100, and the total CO2 emission would go really high. So my suggestion here is that the guides do not only approach specific parts of the project, like saying that you should use electric vehicles here or some really specific points, and really consider the big picture. So we really have to solve the problem, we really have to remove the mess, and therefore it should be a key point of the solution of the evaluation for the sustainability applied to the remediation. Here are my references, and thank you very much.
Thank you very much, Francisco, for this presentation. Considering new approaches, I liked it very much. I think that we'll keep the questions in the chat at the very last moment, where we have the panel discussion moderated by ourselves. So if there's something in the chat, we will ask the speakers at the end. Just by the way, I see Wouter Gewertz as the second chair of our meeting. Hello, Wouter. Then after the next presentation, I will give you maybe the floor to say a bit more about you. Thank you for coming and joining and helping me here. I think we can go to the second presentation, which is a sustainable approach to remediation. So analysis and perspective of the European in the European context, and any rewind experience. So I'm looking if the speaker.
There are two speakers. There are two speakers for this presentation. I'm Silvia Fisario. Yes, I'm an environmental engineer, and I work in Any Rewind, where I deal with sustainable remediation, developing tools to assess remediation strategy according to sustainability and circular economy criteria. Now I'm going to share the presentation. Can you see? Can you see the presentation?
Yes, it's full screen and we hear you well.
Ah, okay. Okay. So good afternoon. It's a pleasure to be here today to share with you the result of a comparative study on contaminated site management between Italy and European and not European countries. In the second part of this speech, I'm going to present the experience of Any Rewind on sustainable remediation. Any Rewind is the E&I environmental company which carries out remediation activity and waste management in operative and decommissioned sites, and we operate applying sustainability and circular economy principles. About the comparative study of this speech, the scope of the study was benchmarking the regulatory and technical approach to identify the international best practice in order to improve the efficiency of site cleanup. And four study areas have been considered: regulatory framework, applied remediation technology, remediation sustainability, and time and cost. Now I give the floor to Mrs. Razzetti, from Stantec, and she will present the outcomes of this benchmark study. Thanks.
Thank you, Silvia. Hi, everyone. My name is Cecilia Razzetti. I'm an environmental engineer and senior consultant at Stantec. And I will talk today as consultant of ENI and consultant of Silvia, of course. A few words about the working methodology of our study. The study was based on a benchmark between 10 countries. We worked on the first phase of data collection among these 10 countries, and then we proceeded with data analysis, of course. The data were collected through the consultation of international literature, the consultation of public reports prepared by sector players, legislators, and public agencies in charge of the management of contaminated sites. We had also the opportunity to interview a number of European agency officials and industry professionals in the countries that we surveyed. Next slide, Silvia, please. So in all the countries we have surveyed, contaminated sites are identified from a list of potentially contaminated sites. So the list of the potentially contaminated sites is the first element to size up the problem of brownfields in a specific country. We started with the analysis of the regulatory framework of the different countries and found out that potentially contaminated sites are those that exceed concentrations of regulated parameters listed in the legislation. And that was the case in all the 10 countries we have surveyed. The higher the number of parameters, the more stringent the criteria for identifying the contaminated sites. For both soil and groundwater, Italy was found to rank among the countries with the highest number of regulated parameters. Maybe you can see the next slide, please. The second element of comparison is the number of exposure scenario considered. So in general, fewer exposure scenario correspond to more restrictive limits. So by making fewer distinctions about the context, the more precautionary condition apply to most cases. Talking about soil, in general, we found 2 scenarios, so commercial and residential exposure scenario. Only in 3 cases, we found 3. So in the UK, for example, commercial, residential, and a third most sensitive scenario, which is garden and lots, is considered. In France, regarding metals, there are 3 toll types to define the guidelines, while in Germany, there are 3 sets of values that are translated roughly into caution, verification, and action values. To this respect, Italy ranks among the intermediate countries because we have the classical 2 scenarios. Next slide, please. About groundwater, in most countries, only 1 scenario is considered. Some countries also consider a separate scenario with the drinking water use. And that is the case for France and the UK. Next slide, please. Another very important element of comparison is how risk analysis is carried out in the different frameworks. Everywhere in our sample, a remediation procedure is started against the occurrence of a risk. So the mathematical models for calculating the risk are very critical and they're not identical. So they introduce further differences between the countries. We have tried to establish a ranking between the countries, considering very specific elements of the mathematical model that are the degree of size specificity of the risk analysis. So either if it's a level 1, level 2, or level 3 risk assessment. We have considered the incremental toxic and carcinogenic risk, which is considered as acceptable by the models, the inhalation rate, the exposure factor, and the location of water compliance point. These are all very specific mathematical aspects of the model. Considering all these factors, we came to the conclusion that Italy is the most conservative country also in the application of the risk assessment. Next slide, please. Another part of the benchmarking study is about the statistical application of remediation technologies in our sample. So we have made a comparison of the most widely adopted soil and groundwater remediation technology. The quality and the way of reporting data is very diverse among the countries, of course. So to make comparison, we had to group the technologies into 3 families. So ex situ on-site technology, so those entailing soil excavation, in situ technologies, and a third family that we called receptor control or monitoring technologies that in the US APA language are referred to as institutional control. So we group the technologies in these 3 families and make our statistic and percentage calculations. So we found out that Italy, France, and the UK are in an average position, in a mid position, as they use a good percentage of in situ technologies. Most of the other countries still rely a lot on excavation for site reclamation. And the US, we can highlight the position of the US because they use a lot monitoring technologies and receptor control techniques to reduce the site. So it's a sort of non-action technology, but they manage to keep using the site under these treated control conditions. Next slide, please. The next point is the sustainability. So this is a big topic, and this has been a big topic in the last few years. We have tried to understand whether in the regulatory framework of the different countries there are sustainability guidelines or either sustainability methods to calculate the performance of the remediation project with respect to sustainability, of course, and to rank, to compare alternative solutions. We have found a diverse situation. So in some countries, there are very specific guidelines that include all aspects of sustainability, so economical, environmental, and social, and they even use quantitative methods. So they can rank alternative options in terms of sustainability and demonstrate how they calculated that ranking. In other cases, there are only qualitative tools, or they're not mandatory, or they just consider one aspect of sustainability, which in most cases is the environmental aspect. The only country where there is no guideline for sustainability is Italy. So we do have elements of this legislation that call for consideration of the sustainability, but we do not have procedures, codified procedures to evaluate projects based on sustainability parameters. Next, please. The last comparison we have tried to make is the economical benchmark. This was the most difficult one. So the comparison of the average cleanup expenditures was very difficult because of the confidentiality of the data, of course, and also because data where available are expressed differently and they're not comparable. For example, we found in some cases cost per cubic meter of remediated soil, or cost per hectare, or cost per site. The most complete study we were able to read is this JRC study that shows that in Europe, remediation cost is in the range of 50,000, 500,000 euros in 40% of the cases. And larger projects that sum up for about 8% of the cases require over 5 million euros. We have reported in the figure on the left the specific data for Italy, and we can see that Italy is in the higher part of the curve towards the right. A direct comparison of the cost estimate per hectare was only possible between 3 countries, so England, UK, the US, and Italy. And also this comparison shows that the highest economic burden is incurred in Italy. Next, please. So this was a very quick overview of this benchmarking study. The outcomes show that Our national situation is more conservative with respect to the other countries for many factors, many criteria. We have strict screening criteria for identifying potentially contaminated sites. We have a larger number of mandatory quality parameters for soil and groundwater. We do have a compliance point for groundwater at the site boundary. We do not have codified sustainability assessment procedure. We bear, as an average, higher remediation cost, and we do not have plans to define priorities for intervention in a portfolio of sites. Maybe Silvia, you want to add something at the end of the presentation? Okay, I'll leave the stage to Silvia.
Thank you, Cecilia. I'd like to share with you the Eni Rewind experience on sustainable remediation. Eni Rewind is committed to increase the efficiency of remediation activities, and for doing that, is adopting an operative model which include 4 main pillars that are represented in this picture. The mobility of contaminants. Eni Rewind is involved in developing a passive sampling methodologies to define the mobile fraction of contaminants, and currently this methodology is undergoing field tests with ISPRA, the Italian Institute for Environmental Protection and Research. About bioavailability and biodiversity, we have developed an ecological risk assessment guideline, and in this session there will be a specific speech on this topic. About circular economy, we operate using technologies and processes which reduce the production of waste, the consumption of materials and energy, and we operate to recover and reuse more resources. And finally, sustainability. Eni Rewind is integrating sustainability in the contaminated site management, developing different tools. A tool for to evaluate the sustainability of a remediation strategy, a simplified tool to assess remediation technology by life cycle assessment, a cost-benefit analysis procedure to estimate the net present value of complex remediation strategy. And we plan our remediation project considering the future site reuse. Since 2011, Eni Rewind is implementing a sustainability program, and the main result of this program was a tool to perform a multi-criterial analysis and compare different alternatives using sustainable objective and indicators. In 2020, this tool was updated to include the life cycle assessment principle and 2 new environmental indicators, balance the 3 pillars of sustainability. So we have identified new socio-economic indicators. We improved the MCA methodology in order to have a more robust tool. And as the previous tool was in an Excel file, we developed a tool that was a web-based application. The result of this update is Astra, the Advanced Sustainability Tool for Remediation Assessment, that is a tool compliant with the ISO standard 1854 about the sustainable remediation. All the indicators included in ASTRA are internationally recognized, and in particular, the environmental impacts are calculated using a life cycle assessment methodology from cradle to grave. And all these indicators are can be associated to the SDGs contributing to UN 2030 agenda on sustainable development. ASTRA could be used for different objectives, for example, to compare, to assess the prescription of the authorities in terms of sustainability, or to evaluate the sustainability not only in the project phase, but also in the construction and the operation phase. And all what we have presented today represent any rewind engagement on sustainable remediation and ecological transition. And we hope that it could be a discussion point with the authorities to improve the contaminated site management and the brownfield requalification. Thanks for the attention.
Thank you very much, Silvia and Cecilia, for this nice presentation. I think there will be some questions at the end. So please stay with us. Now I will invite Wouter to present himself and also to introduce the rest of the session and the next speaker. Please, Wouter, the floor is yours.
Good afternoon, and sorry to be late at the beginning, but I had a call with my American boss, and then you can never say, please leave me alone, which is the reason I was a few minutes too late. So my name is Wouter Gerards. I'm based in Belgium, and I'm one of the Nicole members of the steering group. I'm chairing the Nicole Service Provider Group, and I'm also working for Arcadis, an international engineering consultancy company, where I am trying to coordinate our contaminated plant activities in Europe. So I liked very much the presentation of Eni Rewind and the comments of Cecilia. Looking from a European perspective, I can fully agree with the conclusions you made about the Italian situation. Let's jump into the next presentation, where Kevin Kunze will present how to find the most convenient remediation strategy at a former industrial site. And Kevin is the lab manager and innovation expert at Isodetect, German company, offering isotope analytical services and scientific experience to stakeholders in groundwater remediation. Kevin, I would say the floor is yours. If you could try to find, to finish in 10 to 12 minutes, that would be perfect, so that we can keep enough time in the end for the panel discussion. As to inform you, the session will be automatically closed, so it's not Piotr or myself who will be closing the session. It's automatically done, so we need to be strict on timing. Thank you.
Okay, yeah, thank you, Wouter, and also for this pressure directly from the beginning. So you can see my presentation and my red dot, yes. I hope so.
Yes.
Okay, so let's keep it. Also, the participants number is now really jumping up, so I think now the IT problems are solved. So welcome to everybody. Good morning, good evening, and also thanks to my colleagues' previous talks about Cecilia and Silvia and also Francesca, who nicely introduced that for the remediation of contaminated sites, the aim is always to find the most ecologically, economically, and technically optimal strategy. So I will introduce you how to find the most convenient remediation strategy. So if a relevant biological removal of pollutants can be demonstrated at a field site, a cost-efficient and environmentally friendly remediation options are possible. So what are the steps in that remediation measures to investigate if biological removal or biodegradation is really a remediation option. First of all, of course, you have to check the conditions of the field site, so the contaminant load, the hydrogeological situation, the redox conditions. So are there redox components available for the microorganism that can be used for the biodegradation of the pollutants? Most important, the proof of biodegradation. So qualitatively, in the first stage of qualitatively ways, so compound specific, really especially for the priority pollutants. And most important, it has to be in situ. So you have to examine the area where the hot zones of biodegradation are taking place. As third step, and also if it's possible, to quantify the degradation. Most important to do calculations on the field site models, on the numeric model, on the plume development. So how it's in 15, 20, 30, 50 years, the developing of the plume, if biodegradation is really a sustainable remediation options. And of course, in the quantification, you can do really then degradation, calculate degradation rate constants. And nevertheless, maybe are there options to stimulate this biodegradation processes, so to identify stimulating or inhibiting processes at the field site in situ, and to determine maybe also some stimulant that possibly can be added to the field site to enhance the natural attenuation processes. As you can see with the further steps in this remediation measures, the complexity of this investigation is increasing. So we need really advanced monitoring tools that has to be applied, most important, in parallel. So in the case of a multiple line of evidence approach and in the early stage of site characterization. The advantage of such a multiple line of evidence approach is the mutual validation and to use the really single the advancements of each method really to have a well-funded site characterization. So what are those advanced monitoring tools for remediation methods? You have qualitative tools like metabolite analysis, so analyzing transformation products, intermediates within the degradation processes directly in situ. So you have proved that there biodegradation is going on. Otherwise, you didn't find such intermediates. You can analyze or also isotope analyze of the redox components, for example, nitrate, sulfate. And if you can really prove that there's sulfate reduction, nitrate reduction going on, then you can really have a proof that there are microbial processes most important connected to the pollutant degradation. And of course, you can do GC fingerprints, either with FID or mass spectrometry, to really set up some ratios between compounds that are known that are more recalcitrant or degraded area. And with this change in this GC fingerprints, you can really have proof of biodegradation. Most importantly, you have quantitative tools like the semi-quantitative tool Qpcr Analysis, targeting genes or functional genes of degraders that are known to degrade those pollutants. And the most convenient tool is the compound-specific stable isotope analysis, so also our main tool. So you will analyze the isotope fractionation, and with this tool, you can really do calculations on degradation rate constants. With lab microconstants and also in situ microconstants, you can also investigate highly sensitively pollutant degradation, but you can also investigate if some stimulation options are possible. I want to focus now on the three methods here in the semi-quantitatively tool with the example of a former industrial site in Germany. The site was contaminated by mainly chlorinated volatile organic compounds, so mainly PCE, tetrachloroethene, TCE, trichloroethene, DCE, and vinyl chloride, on slightly contamination by BTEX and pHs. At this field site, we have potentially several sources of contamination, and we have general anoxic conditions. So the reductive dechlorination is supposed to be the main processes in biodegradation or in degradation of the chlorinated ephenes, in which the microorganisms are using the chlorinated ephenes as a terminal electron acceptor in their respiratory chain. And therefore, with the third step, the chlorine atom is exchanged with a hydrogen. And you have a degradation from PCE or TCE to DCE to vinyl chloride, and most important, to ethene, the non-toxic product in this complete degradation. So the aim of this multiple line of evidence approach or of this investigation was really to investigate if you have complete pollutant degradation processes already going on and active at the field site. And we wanted to evaluate if different remediation scenarios are possible. So monitored natural attenuation, or maybe is there also possibility to enhance potential natural attenuation processes, and how's the future development of the contaminant plume. The field site you can see here, and with the PC and TCA load, and here in the north you will see that we have here area, this is a lake, so where with this area that has to be protected from the contaminant load. The PC and TCA load at this field site, as you can see here, was with up to 500 and 1000 microgram per liter, and as you can see we have already maybe 2 potential sources of contamination due to this contaminant load at this industrial field site. The DCE load, so the dichloroethene, a transformation product of the PC and TCE, was we have the plume of this TCE load already reaching the area that has to be protected, and also the main sources or the main sources of these potential 2 sources of contamination. And we already detected vinyl chloride at this field site, a further degradation profile as DCE degradation with the and special development of the plume, as you can see here. So we want to investigate the pollutant degradation processes actively at the field site. And the first step, by Qpcr analysis, you are extracting DNA, and as you all know, the DNA is the carrier of the genetic information. And with Qpcr analysis, you're targeting either functional genes, and these functional genes are encoding enzymes, so proteins that are catalyzing certain degradation processes. In our case, it will be the enzymes catalyzing the steps in the reductive dechlorination. Or, and as an addition, you can also target on taxonomic genes. So those genes are encoding groups of microorganisms that are known to catalyze certain degradation processes. So specialized microorganisms, for example, catalyzing the reductive dechlorination. So we extracted DNA from several sediment samples. And first of all, the first potential source zone, the source zone 1 and 2 filter section, you see that we detected genes of a special group, so-called D-halocogoides. And D-halocogoides are one of the most important group of microorganisms that are able to degrade completely PCE and TCE to ethene as a non-toxic product. So with the detection of those special group of microorganisms, we already have proved that their degradation of the chlorinated ethene is going on. And as an addition, we also detected a special enzyme or gene encoding an enzyme catalyzing the last most important step from the highly toxic vinyl chloride to the ethene with the vinyl chloride reductase. We didn't detect any BTEX degraders or aerobic chlorinated ethene degraders in the source zone 1. In the second source, in both filter sections, we additionally also detected the halocogoides. We didn't detect it, the function gene of the vinyl chloride reductase. Maybe it's a hint that the vinyl chloride degradation is limited at this place or this situation. But nevertheless, we detected also the halocogoides, a special group of reductive dechlorinases. So we already have a first proof that the biodegradation of chlorinated ephenes is taking place at this 2 source zone. Further downstream, we didn't detect any D-halocogoides or vinyl chloride or others. So there's really the question if this further downstream groundwater wells, maybe there is no degradation, no biodegradation of chlorinated ephenes going on. So with a second method, with the isotope fractionation, we investigated how for the compound-specific degradation processes going on and tried to calculate also those degradation processes. The compound-specific stable isotope analysis is analyzing the isotopic ratio, and this ratio is the ratio between the heavy and the light isotope. Certain elements have different isotopes, so we have a stable isotope. So in fact, the example of the carbon you can see here, we have a heavy isotope, so it has 1 neutron more than the light isotope, and we are analyzing the ratio of this isotope in respect to internal standard. And you have a natural abundance of these 2 different isotopes, the light and the heavier ones. And the basic of the isotope fractionation is that pollutant molecules with a heavy isotope in a molecule are degraded more slowly and accumulate in the remaining pollutant fraction. The reason for this is that the activation energy in the bond breakage, if there's a heavy and a light isotope, is higher than if it's only 2 light isotopes. So in consequence, with the certain degradation of the contaminant, all the molecules that have a heavy isotope in the molecule are still remaining in the pool. So the ratio of the 13C to the 12C in the remaining pool is increasing due to the further degradation of the contaminant. So the isotope ratio is shifting towards more positive isotope values, as you can see here, from -30 around to -25 per mil. So what the takeaway, what was the take-home message? That in case of degradation, just remember isotope values are getting more positive.
We have one more minute left, Kevin.
Okay, we have to. Okay, so yeah. Okay, thank you. So we investigated different wells, groundwater wells, and we investigated the isotope values. And as you can see here in the source one, we have the some isotope values of about -18, -16 per mil, and further downstream, we have a shift towards more positive isotope values. And this is already proof that degradation is going on along the groundwater flow path. Further on, when reaching the second potential source of contamination, we have then a shift again to more negative isotope values. And a shift to more negative isotope values is not possible due to degradation or any processes. That's why we have here proof that we already have 2 additional secondary sources at this field site. Further, we have again a shift towards more positive isotope values, as you can see, from -23 to -6, -15 per mil, whatever. But with this, we have a proof of degradation from this second sources that the chlorinated are degraded. And with this shifts in the isotope value, we can determine and we can quantify first order degradation rate constants. And we can calculate forecasts of the development of the plume. And as you can see, with a forecast without any remediation after 50 years, you will see that the PCE, TCE, and DCE will be completely degraded. However, the vinyl chloride will be with 10 to 50 microgram per liter still present and is reaching already the area that has to be protected. That's why we investigated additionally also if there may be some stimulating effects possible. And this we investigated by lab microcosms. And this were special cases of lab microcosms because here we added 13C labels. So only microcosms, copollutants that are labeled with the 13C, chemically labeled. And the advantage of this is when you're adding this to your microcosms and they are degraded by the microorganisms, you will see it in the end products, in the mineralization product, here in this case CO2. And when you have a shift in this isotopic ratio of the CO2, you have a highly sensitively proof that degradation is going on. And you can really do different lab microcosm setups, adding oxygen, lactate, iron, whatever you prefer. And then you can compare to each other. You can calculate it mineralization rates. This we did. Yeah, I will come to my end. This we did to still 2 minutes left, sediment and groundwater. And I added oxygen and the 13C level chloride and vinyl chloride. And as you can see, after 100 days of incubation, we have an increase in the isotope ratio. And with those, we have really proof that with the addition of oxygen is a possible enhancement remediation option. We can calculate the first order mineralization rates and implement it in our field site model. And as you can see, when we were able to implement it here in aerobic zone with oxygen injection, we were decreased the amount of vinyl chloride at this field site is not reaching then anymore the area that has to be protected. In summary, we detected just shortly 3 distinct sources by compound-specific stable isotope analysis and also sustainable natural pollutant degradation processes. We determined degradation rate constants, and in order to assess the effectiveness of a possible aerobic treatment, we investigated by 13C microcosm studies. And with the help of this model calculations, site-specific remediation scenarios, monitor natural attenuation, as well as enhanced natural attenuation scenario were possible. I want to thank you for your attention and my colleagues from HPC and also my colleagues from ISODetect. And if you're interested, it was now really fast because I have to hurry up a little bit, still within the 15 minutes, sorry, Walter, that I didn't manage to be in the 12 minutes. However, if you're interested in if you have more time, going more deeper into it, I can recommend a webinar taking place next week. And Thursday, you can either use this QR code or you can just write me email. Thank you for your attention.
Thank you very much for this interesting presentation and also the fact that you use different methods, as one method alone cannot be can give it a contradictory indication. So the fact that you use several methods confirms the overall biodegradation, which is always an interesting approach, according to me. So thanks again. We will move to the next presentation of Russell Thomas. I mentioned to you already that I'm active in Ecol. Well, Russell is also very active within Ecol. He's one of our leaders in the innovation working group. So really a marvelous presenter. He's working for WSP in UK. He's linked to university as well as a professor, and he will tell us about the development of gasworks and how this can inform site investigation, remediation, and heritage. Russell, floor is yours. And we see your screen.
You can see it. You can see the screen, okay?
Yeah.
Yeah, okay, great. So thank you very much, Wouters, for the opportunity to speak at this wonderful event. I'm hoping to distill into my allotted time some of what I've learned over the past 24 years working on gasworks. So I started my career in industrial research in 1997, developing sustainable remediation techniques for remediating gasworks, which was quite a new thing at that time. I moved into consultancy in 2001. And since then, I've been working on a mixture of site investigation, remediation, and research projects. So as part of that, it's led to quite a detailed knowledge of these gaswork sites, and has led me much into learning about the history and the science and engineering behind it. And this knowledge has been recycled back into doing work, research, site investigations onto gasworks. So if we go back to what manufactured gas is, it's very different to the natural gas which we use today. The main difference was that the gas was primarily hydrogen, carbon monoxide, and methane, whereas the natural gas we have today is primarily methane. It also, the gas manufacture process also produced a lot of byproducts, so coal tar, mannacal liquor, and purifier wastes. And I'll talk a bit more about coal tar in my presentation. This is a simplified schematic of a gasworks. So the coal is delivered from the mine to the retort house where it's heated. The gas is then purified. So coal tar is removed by condensing. Washing processes remove the phenol and ammonia-rich liquor, and then hydrogen sulfide and cyanide are removed from purifiers. In some cases, benzol was also removed before the gas was then distributed to customers. This drawing gives you an idea of the development of the gas industry. First public gasworks was in Great Britain, started in 1814, and then the gas industry spread across the rest of Europe, and then globally. Local engineers learned from British companies which set up gasworks. So the first gasworks in Germany and Austria were both set up by the British Imperial Continental Gas Association. And as this knowledge was transferred to the continent, then their own local gas engineers set up their own companies and works. So it became a huge European and then global industry. In terms of the extent of the industry, it was predominated in Great Britain, France, and Germany, but you'll find gasworks in every European country. There's a lot of information available on these former companies, and you can see here the Tuscan Gas Company was one British company which operated a number of gasworks across Italy, and there are also other British-owned companies that own gasworks across South America. There were gasworks across what was the former British Empire, so Australia, Canada, New Zealand, all adopted the same technologies that were developed in Britain. And then countries such as Japan adopted initially European technologies to develop considerable gas industries. So apart from Antarctica, there was gasworks in every continent in substantial numbers. The technology, there was a wide range of companies, British, German, Italian, French, Belgium and the Netherlands as well, all making and supplying gas manufacturing plant. And this just gives you a few ideas of some of the adverts. British companies exported that technologies, and British gasworks also imported technologies from abroad, particularly France and Germany. This slide just gives you an idea of the complexity of different processes used on gasworks. So in the top left-hand corner, the low temperature horizontal retort is where the technology originally started. Increasing mechanization, improved materials for making the retorts, and improved methods of heating the retorts allowed more mechanized, higher temperatures to be produced. which had an effect on the tars produced. In France, the incline retort was developed, which gave a slightly different thermal gradient across the retort when it was heated, and that used gravity to help move the coal. And from Germany, the vertical retort was first developed, which was then further adapted in the UK. In America, they developed a method of making gas very quickly called water gas, which could then be enhanced by injecting oil into the carburetor in the system, which made a totally different form of tar to what you find from the coal-based processes. Then from the continent, from France, Germany and Belgium, the byproduct coke oven was developed, which was a way of making primarily coke, but byproduct was gas, which was used to supply a lot of domestic gas networks, and also the coal tar. Coal tar was produced there. The chamber oven was developed in Germany, and that became particularly well established across continental Europe as it suited the coals available. And then oil gas is another method, primarily used in the mid-20th century, making gas directly from coal. And then there's a few other variations on this. You can see from this chart here, it shows the impact of the different temperatures. So the original low temperature processes produced gas around 600 degrees. And then the later coke ovens and high temperature horizontal retorts produced gas around 1100 degrees. And the inclined and vertical retorts operated at temperatures between these, depending on the exposure of the retort to the furnace or producer. More importantly, when you're looking at coal tars, which quite often are the main contaminant on the gasworks, this same effect of heating also affects the composition of the tars that you may be driving. So an increase in temperature decreases the volume of tars, but it does so in a way that it removes most temperature sensitive substances such as paraffins, naphthenes, and olefins, and some phenols as well, predominantly to things such as PAHs, which are more stable. The study that we did at the University of Strathclyde, we managed to collect a number of coal tars from sites across the UK and some from Europe and the USA, where we had knowledge of the site's previous use and operations. And we could correspond that when we analysed the samples using two-dimensional gas chromatography with time of flight mass spectrometry, that the actual samples actually can be grouped using principal component analysis relative to their level of thermal degradation. So the coke ovens plot at the highest, and the vertical retorts, which have slightly different signature because they have both high and very low thermal degradation across the retort and the vertical plane. These plot at the bottom. And as you may expect, the oil signatures of carbureted water gas or creosote plot quite differently. This research also showed that there were 2,369 individual components we could detect within the coal tar, but only 173 of these were common compounds found in all of them. You can see here marked in the red are the US EPA 16 pH. Those in the yellow are the US EPA 32 pH. And then those are shaded in purple, blue and green are the nitrogen, oxygen and sulfur heterocycles that you find in pHs. And it just shows that tars have a very diverse composition. At peak tar production around sort of 1948-1950, the UK was producing 2.4 million tonnes of coal tar. And this slide just shows you that it was coming from a range of different processes, with all these different processes having slightly different chemical characteristics of their tars. And this slide just gives you a breakdown of the various composition of some of these tars. So you can see relative levels of pHs and things such as aliphatics vary quite significantly between the tars. And this paper you can find online. So some of the implications of this work that we did were that typical analysis and risk assessment for pHs is primarily based on BAP, but there are many alkylated pHs, nitrogen, sulfur, and oxygen heterocycles present in tars that we don't typically look at. And
could you finalize in 1 minute about?
Okay.
Yeah, time flies.
I'll just go. Noted with carbonization temperature, tars become more viscous, and the concentration of parent and nitrogen, sulfur, and oxygen heterocarbon cycles increase. You can find coal tars in many forms. You can find them mixed in soils with tanks, dehydrated with ash on site, or free phase either in tanks or within the ground, strata, or trapped in rocks. This is what you would expect to see with a carburetor water gas tar. This is a much more mobile L or N NAPL, able to move in with the water table. It's very different to what we typically expect on gasworks, where you have the D NAPL that sinks to the bottom of the aquiclude, and there's limited horizontal migration except for diffusion. Just another point on different, you can refine coal tars, you can distill them, and if you distill them, the coal tars on the site that had a chemical works will have totally different properties, just the pure coal tar. So you have to be careful that they may be quite different. I won't dwell on this, but it's worth looking at in the notes afterwards. Gas holders are one of the main features you find below ground on the site. We typically find below ground water sealed gas holders, and these tend to have either a flat base or a dumpling, as you can see in this picture here, a mounded center with an area of sludgy tar around the edges. So when you're investigating these structures, you need to be careful and ensure that you're investigating the annulus where this tar may be found. And there's a useful document on the Clare website that's got a lot of details about gas holders. And then just finally to finish on, as I mentioned, gasworks, one of the original industries. I carried out a study for Historic England where we investigated over 3,600 sites, find out about their history and their surviving state. As part of our job as contaminated land professionals, we do have the ability to identify important industrial sites and be able to advise about how we can bring these back into beneficial reuse, rather than just saying the cost of preserving the heritage is too much and flattening them. So it's worth remembering. So I'll finish there. Thank you. Sorry for going slightly over.
Thank you very much for always interesting presentations of yours on gasworks and the history of gasworks. It's tremendous what you have in your experience and in your brain, I would say, from all the history of these gasworks. We will now go to the next presentation on contaminated sites prioritization in the Republic of Serbia. It will be a presentation by two people, Mr. Jeftić and Mrs. Kukobat. I give you the floor and for your presentation.
Thank you. I just need to share my screen with you.
Yeah, we see it and we hear you.
Okay. Good afternoon to everyone. My name is Nemanja Jeftić. I'm coming from ARUP office in Belgrade, and today with my colleague Lana, I will present you contaminated site prioritization in Serbia. First of all, this investigation of 32 contaminated sites was done under the project Enhance Cross-Sectorial Land Management through Land Pressure Reduction and Planning, financed by GEF and implemented by a Serbian Environmental Protection Agency. With support of United Nations Environmental Program and Italian Ministry for Ecology and ISPRA Institute. This project was conducted in the period of 2015 until 2019. We had no information when we started this. We had almost no information on locations that are going to be investigated. And we went through several stages until we get the final results. First locations were chosen from inventory of contaminated sites managed by Serbian Environmental Protection Agency, and in that time that inventory had 309 potentially contaminated sites. From those 309, for the site visit, for the first site visit in 2016, we chose 37, and from those 37, on 32 locations was conducted soil sampling, and we gathered information such as current and previous land use, surface area, type of industry that was on that location, type and the quantity of hazardous substances, and soil and groundwater quality, which was conducted on those locations. As I said, in 2016, we went through these 37 locations, and on 32 we took soil samples. Next year in 2017, and we took 264 soil samples were analyzed in that period. The most important thing on in the first site visits were that we found source of pollution, potential receptors of pollutions, and potential exposure routes of that pollution. And also after that, we prepared programs and strategies for soil sampling. As you can see, those are photos from the soil sampling in 2017. I have put here a couple of photos of locations that we have visited during 2016 and 2017. For me, most interesting are those two photos. It's a river in eastern Serbia that goes through core mine in eastern part of Serbia, and the river just go through that mine and comes out completely polluted. So the soil and the area near that river, when the water is a little bit higher, it looks like everything was burned during some fire in a forest. And the other photos are from different locations that we have visited. Some of them are abandoned, as this one location, but this location is still working. The important is to say that we used XRF portable device. We used this with help of our colleagues from Italy, and by using this portable device, we reduced the number of soil samples that we have taken the next year, because we focused mainly where the most of contamination is located. So I would like to mention that one of the outcomes of this project was also development of Cadastral of contaminated sites. The Cadastral is now maintained by the Serbian Environmental Protection Agency. And the idea was that all information about potentially contaminated sites in Serbia was fulfilled in this database by the local self-governments or municipalities. And we put also these 32 locations that we have conducted a survey. And the important thing is to say that it's not necessary that you can enter different level of information in this cadastral. For example, if some location, you can enter just location, name, type of industry, geographical coordinates, and that's it, if no survey has been conducted on that area. So now my colleague Lana will tell you more about site prioritizations. Lana, here.
So good afternoon, I'm Lana Kukobat, and I will take over from here to present you the next phase of this study. It includes the site prioritization. So basically, according to all data that we collected during the site investigation process, we systematized those data and established several criteria for site prioritization, the first step of site prioritization. And these criteria are listed here on this slide. So according to them, we divide all 32 locations in 4 groups. In group 1, we have locations where contaminants did not exceed the remediation values. In group 2 and 4, we have locations that additional monitoring and more detailed research are proposed at this time. And this is especially for group 4, that covers large industrial enterprises, where only certain parts of the complexes require remediation. So our focus group is group 3. And after identifying 14 locations as with highest priority for soil remediation programs, we decided to also compare them and prioritize them from the aspect of risk to human health. So for this purpose, we choose the preliminary risk assessment model for the identification and assessment of problem areas for soil contamination in Europe. In short, the PRAMS model or the PRAMS methodology. And this methodology was chosen since, well, it was created in 2005 within the EEA's project that aimed to develop a tool that can facilitate the assessment and the classification of contaminated sites, and in that manner to support the national, regional, or local programs for remediation of these sites. So how does it work? Well, for the design of the conceptual site model, go back. So for the design of the conceptual site model within this methodology, it was adopted a paradigm: source, pathway, and receptor, where source represents a contaminated soil or disposed waste. The receptor is human health, and exposure pathways are the groundwater, surface water, air, and direct contact. As for the scoring system, the PRAMS model calculates relative risk according to the scores assigned to the values of the relevant perimeters for each location. This model is developed in the access environment, and from our experience, it was a very user-friendly tool. But the most complex part was certainly the collection of required perimeters for Tier 2 rank of the relative risk assessment. And these perimeters are listed on this slide, and during our site investigation phase, we managed to collect the majority of them. So after entering available perimeters into the PRAMS model, the priority list was compiled, and the results of PRAMS calculations are shown on this table. Also important to emphasize is that within the PRAMS methodology, the classification of risk values and the uncertainty factor is proposed. So according to the classification, out of 14 allocations, first 3 are in the high risk class, and the rest of them are in the medium risk class. As for the uncertainty factor, all of them belong to the low uncertainty factor class. That means that the majority of required perimeters were entered and available for calculation. On the right side of this table, you can see exposure pathways, and they are ranked according to the values calculated within the PRAMS application. And after applying this methodology to our 14 locations identified with highest priority, we drawn several conclusions. And the key ones are that this priority list, according to the PRAMS methodology, can be used for the decision-making process. and risk-based argumentation for better allocation of available resources for remediation programs. Also, application itself opens several possibilities to enhance the management of contaminated sites. On systematization of data and possibility to identify missing data is especially helpful when we need to compare and assess a larger number of locations. And also the PRAMS model give valuable information on explored pathways. They can serve for a kind of risk communications in the process of management of contaminated sites. And as for the possibility to apply this methodology to other sites registered in the Cadastral of the Republic of Serbia, during this project, an important legal act was adopted, and the rulebook is developed to enhance the management of Cadastral, and it contains forms and questionnaires about site perimeters that are also the basis for application of the PRAMS model. So finally, the next step forward will be to develop remediation programs for 14 locations according to the PRAMS model, and also to try to apply this methodology to other sites registered in the Cadastral. We will be available for all your questions at the end of this session, and we wish you to enjoy the next presentation, and thank you very much for your attention.
Thank you for the excellent presentation, and it's always interesting to see that we still have a lot of work to do. And looking at the pictures, I believe it's still a lot of work. So thank you as well for this overview. Piotr, you take over again?
Yes, I can take over. Thank you very much, Wouter. I would like also maybe to mention, I think at the beginning of the session, there were some IT problems. Some people could not join us. I propose that during the panel discussion, the first and the second presentation and presenters present just one slide with some short conclusions. So just to let the public know what it was about, and then to have some problem remediation. Now we can go to the next presentation. It's Jose Carlos Gueva. He's geologist, specialized in contaminated land management and hydrogeology, and vice president of the Industrial Committee of NICOL for the Latin America. He will be presenting the development of an integrated management strategy model for acid mining drainage in contaminated areas due to historical coal mining activities in southern Brazil. So please, Jose, the floor is yours.
Thank you, Brian. So the coal basin of Santa Catarina state includes an area over 900,000 acres in southern region of Santa Catarina state in Brazil, involving 24 municipalities located between the towns of Araranguá and Lauro Miller. It contains a reserve of mineral coal around 4.3 billion of tons, corresponding to 13% of country total exploitation. The exploitation occurs mostly in three coal layers, economically viable, named Barro Branco, Irapuá, and Bonito, associated with Permian sedimentary successions of Paraná Basin. The coal mining activities began in the early of last century and had a considerable expansion after the Second World War. It remains locally important to the local economy setting until to the present. The coal production was initially used to generate vapor in ships and as a fuel supply to locomotives. And after the 40s, it started to be used primarily in steel industry. Since the 90s, with the higher sulfur content and the opening of local economy, most of domestic coal production in Brazil has been used for power generation at Central Termoelétrica Jorge Lacerda in the city of Capivari de Baixo in Santa Catarina state. Meanwhile, important coal has been used for the country's steel-making industry. Until the early of 90s, before privatization of Companhia Siderúrgica Nacional, owned over 70,000 acres of coal reserves, where it developed the largest superficial and superficial mining activities, processing units, waste landfills, transportation, and other diverse coal mining related activities. During this period, the Barro Branco and Apuá formation were exploited, and due to the metallurgical characteristics, the coal was extensively employed in the first integrated steel making in Brazil, placed in the city of Volta Redonda in Rio de Janeiro state. From 91 to 2000, CSN began to closure mining program in the entire region, where the main assets were sold to third parties. As a result of this operation, more than 1,210 acres of subsuperficial areas and 2,400 acres of subsuperficial mining areas divided in 33 units, 46 mining entrants in 7 different municipalities were officially recognized as a contaminated land over legal responsibility of CSN. Besides CSN, other 70 mining companies had operated in this region during the same period, contributing to generation of acid mining drainage. In total, this operation resulted in more than 6,000 acres of superficial mined areas and 16 acres of subsuperficial mined areas, 820 abandoned mining entrants identified to the present. That results in several regional impacts to the environment. So the main objective of this project was the development of an integrated management strategy model for acid mining drainage, contaminated areas under legal responsibility of CSN, to historical coal mining activities in Santa Catarina state. Due to factors such as large extension, geological, and stakeholder complexities, several of the areas can be classified as complex sites. Typically, at complex sites, remediation progress is uncertain, and remediation is not anticipated to achieve closure or even long-term management with a reasonable time frame. Both technical and non-technical challenges can limit remediation. So considering these challenges, it's necessary to employ a concept that have been recommended to manage complex contaminated areas, described by ITRC as adaptative site management. This process is comprehensive, flexible, and interactive. It's well suited for sites where there is significant uncertainty in remediation performance prediction. Adaptative management includes setting short-term interim objectives and long-term sites objectives that reflect both technical and non-technical challenges. The remedial approach may involve multiple technologies and any on time and changes in technology over time. Comprehensive planning and the schedule evaluation of remedy performance help decision makers track remedial progress and adjust the remedy, if needed, to stay on track to achieving short-term interim objectives. Long-term planning can also improve the timeliness of remedy optimization, reevaluation, or transitions of other technologies or contingency actions. From this concept, the main initial tasks adopted to the development of integrated management strategy model for acid mining drainage contaminated areas were revision and organization of available data regarding previous environmental studies performed at the site, presentation and short description of successful case of environmental management in sites with similar issues that adopted criteria to prioritize areas for soil and groundwater remediation. Site visits, identification of data gaps regarding the site conceptual models, classification of the siting regarding complex aspects and site conceptual model development, elaboration of investigation plans of different areas of concern,
ranked according to the urgency, consolidation of strategic long-term plans, and continuous dialogues with key stakeholders. As a result, integrated strategy management for acid mining drainage contaminated areas under legal responsibility of CSN has been evolved and evaluated. As a result for this proposition is the recognition that the most advanced global practices for environmental management of mined areas have similarities with strategy employed for management of contaminated areas. This approach is focused on development of robust conceptual site models and the quantification of ecological and human health risks that leads the proposition of intervention plans, with objective to recover the natural environment at mine degraded areas. It also recognizes that adaptative site management concept is well suited for acid mining drainage, contaminated areas that reach the objective of intervention plan. So to finalize my presentation, I would thanks to Companhia Siderúrgica Nacional, my colleagues from USP, the Professor Reginaldo Bertolo, and my colleague Sasha Tonhart, and Nicole Latin America as well. Thank you very much.
Thank you very much for this interesting real case study. There might be some questions at the end. Please stay with us. We can go to the next and the last presentation. Sylvia and her colleague Elisa will be presenting on ecological risk assessment for contaminated site, guidelines and path forward. Please, Sylvia, you might be
yes.
restarting, yes?
Yes, okay. I share the screen. A brief introduction. My name is Silvia Frisario, and I work for AnyRewind, where I deal with sustainable remediation. Can you see the screen?
Yes, we can see the screen, not in the presentation mode yet.
Now, okay.
Yes, it's in the presentation mode now.
Okay. Today, Mrs. Jubilato and I will present the result of a long-term collaboration with between AnyRewind and Ca' Foscari University of Venice. The topic of this speech is the development of an ecological risk assessment guideline. But I have some problem with the slide. Oh my God.
It does not go forward, or
no?
Maybe click on the slide with the mouse and then try with the.
I do. Okay. 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 AnyRewind is the environmental company of ENI, and we operate in various different area and sites. And for this, we apply different drivers on our integrated approach for remediation, such as mobility, bioavailability, biodiversity, sustainability, and circular economy. No, okay. In particular, in ecological sensitive areas, the contaminated site should not only be managed based on the observance of limit values set by law, but a multidisciplinary study should be applied, such as the ecological risk assessment, to evaluate the chemical contamination impacts on the ecological receptor, or the effect that the remediation activity could have on ecosystems. In Italy, ecological risk assessment is not a legislative requirement, and we don't have national guidelines. Therefore, any rewind has decided to develop a general guideline applicable to different environmental matrices in collaboration with Qpcr University. The starting point from this collaboration was the any rewind experience on the management of Lake Maggiore sediments, where an ecological risk assessment was conducted in collaboration with the different stakeholders, such as university, ESS, the Italian National Institute of Health, ISPRA, the Italian Institute for Environmental Protection and Research, and the Regional Agency for Environmental Protection, and CNR, the National Research Council. Now I give the floor to Mrs. Jubilato, who will explain better than me the result of this ecological risk assessment guideline. Thanks for the attention.
Okay, thank you very much, Silvia. I'm Elisa Giubilato from the University Ca' of Venice with a background in environmental risk assessment and management and its application to the management of contaminated sites and environmental resources. So as probably you know, the ecological risk assessment is an iterative and structured approach to evaluate the likelihood that adverse ecological effects are occurring or may occur as a result of exposure to one or more stressors. In several countries, ecological risk assessment is considered as a tool to support the management of contaminated sites in case the presence of ecological values is identified. And ecological risk assessment is aimed at better addressing and optimizing the strategies, efforts, and resources for site remediation. For the development of our guidelines, we started from a review of the existing ecological risk assessment guidelines in the international context, looking both at the European and not European countries. We then proceed to a critical evaluation of tools and approaches available in this document to select those that we consider more easily applicable and suitable to our context. So the final result is are these guidelines for the ecological risk assessment of contaminated sites, which were completed in 2020. We, according to the recommendation of existing guidelines, we adopted the typical framework for ecological risk assessment, which is composed of a problem formulation phase, followed by exposure and effect assessment, and finally by risk characterization, where the outcomes of previous steps are integrated and jointly evaluated to achieve a conclusion on the probability and magnitude of an ecological impact in the contaminated site. And the result of this process is aimed at providing information for the optimal risk management. We decided to adopt a tiered approach, which is typically suggested both for human health and ecological risk assessment. And we consider as well the weight of evidence approach as one of the leading methodology, because it allows to evaluate multiple sources of information and to achieve more robust conclusion on the risk assessment. Silvia can, thank you. So I cannot go through all the guidelines in detail, so I will try to give you a taste of what we have included in these guidelines. So the guidelines consist of a main report and 4 annexes, which were developed with the idea of providing a risk assessor with practical tools to support the implementation of ecological risk assessment. The main report provides a description of the framework we proposed for ecological risk assessment, and it starts from the evaluation of the presence of valuable ecological receptors to be protected at the site. Ecological receptors could consist in habitat, so fragile habitat, for example, species, including the rare species, or also ecosystem services. In case these receptors are identified, the risk assessor should proceed with the review of existing information about the site, should identify at least preliminarily the relevant exposure pathway, and based on the information, he can develop a conceptual site model. So the final aim of this step, which is basically the problem formulation step, is to assess whether there is a relevant link between contamination and receptors. This is what we have included in the, can be found in the main text of our guidelines and in Annex 1. In this step, it's necessary to identify which are the protection goals. The risk assessor should select measurement and assessment endpoints, as well as lines of evidence to be evaluated and investigated. And in this phase, it's also necessary to develop a sampling and analysis plan. So once the problem formulation step is concluded, it's time to proceed to the exposure and effect assessment. And then, of course, to integrate the result into risk characterization. According to a tiered approach, as a first step, as a first year, we can have a screening ecological risk assessment, where, for example, the existing data can be evaluated against the protective screening values. In this phase, in this tiered, data gaps and uncertainties should also be identified so that they can be, in case, better investigated in a further assessment. So the final question of first year risk assessment is whether there is any potential ecological risks. In case, at least for some receptor, this risk has been identified, we should move to a tier 2 ecological risk assessment, which is a detailed assessment, and which foresees the let's say the refinement of previous of the conceptual site model previously identified, and as well as site-specific investigation, or for example, the identification and development of site-specific toxicity reference values. So in the end, the outcomes of a tier 2 ecological risk assessment should answer the questions, are risks, ecological risk at the site unacceptable or uncertain? Is there any evidence of relevant effects? If the answer is no, we can stop, and in case implement a monitoring plan. If the answer is yes, we should move to the assessment of the causal link between contamination and ecological effects. On the right side of the slide, you can see the indication of the annexes where where specific tools like tables or checking lists are provided to support the specific tiers, and also to support the assessor deciding whether to move to a next tier or not. So, as in any type of assessment, there are many questions which can arise during the assessment. the risk assessors face many doubts and many questions about the relevant information to be included in the assessment, how to identify data gap, or how to measure, for example, in the case of ecological risk assessment, specific effects or endpoints, which are the best tests to obtain this answer. So to support the practical implementation of an ecological risk assessment, we decided to include in the guidelines a set of annexes which have the practical goal to guide the assessors in the different steps. And so I will give you just some example. In Annex 1, for example, we have included a list of tables like checklist and templates. For example, if you see the table 4 is a template for the identification of exposure pathway for aquatic ecosystem, and on the right side of the table you can see which are the steps where this tool can be used. So in this case it's for the problem formulation step. Or for example, we have developed, maybe possibly adapted from other international guidelines, template to summarize the evaluation of lines of evidence in a weight of evidence approach, and this is typically useful during the risk characterization phase. Please, the next. In Annex 2, we focused on toxicity reference values and screening values. So we described approaches that can be applied to derive these reference values. We propose a selection of existing values that can be used as screening values, like the environmental quality standard, which exists for both fresh water and transitional and marine waters. And there is also a specific chapter to define, to suggest how to define a site-specific toxicity reference value in case it's needed, looking at the specific conditions of the site and of the available toxicity test and ecological surveys. In Annex 3, we propose a kind of framework to guide the selection and evaluation of toxicity testing, of ecotoxicological test, based on the, let's say, assessment goal, site-specific condition, target receptor. And this annex also includes some general consideration and indication for the interpretation of toxicity test result, which is always a very critical step in ecological risk assessment. And finally, in the last annex, we have included indications on how to evaluate the causal link between contamination and ecological effects. So there is a framework with the indication of all the tasks to be, let's say, performed, starting from the listing of all possible causes of effects, then an explanation of the available methods for evaluating the causal link in the experimental design and in field investigations, for example, on how to identify confounding factors. There is a suggestion for approaches for data analysis. And finally, some recommendation on how to implement weight of evidence approaches, so how to evaluate and integrate information coming from different lines of evidence, like chemistry, ecotoxicity, and ecological surveys. So in conclusion, In our vision, the application of these guidelines could suitably support the management of contaminated sites where an ecological value has been identified. And the aim is to find a balance between environmental protection and the, let's say, more effective remediation strategy. The proposed guidelines currently are being tested on 2 any rewind sites where the contamination is potentially affecting different matrices, so that we can test the proposed approach also on different environmental matrices, in particular in the cases at end. We're dealing with the sediment and soil contamination. And our objective is to test these guidelines and to identify possible weaknesses in the procedure, and to so that we can finalize the guidelines and to finally disseminate them at the national level. As a possible roadmap for the future, the final aim is to share these guidelines with the main stakeholders in the remediation sector, especially with environmental national authorities, and to look for the endorsement of stakeholders so that it will be possible to regulate the ecological risk assessment and to find a place for ecological risk assessment in the national regulatory context. Of course, this is, let's say, quite ambitious, but we hope that this work could represent a useful step in this direction. So that's all from my side. Thank you very much.
Thank you very much, Silvia and Elisa, for your presentations. I think that from you, it's clear that you're trying to integrate the sustainability and circular economy principles into contaminated sites management. It's from Silvia, and environmental risk assessment that is there to support the management of contaminated sites from Elisa point of view and work. So thank you very much for this. I think we can now go to the panel discussion, and as a first task, I would ask Francisco, if he's available, to present one slide with conclusions from his presentation, since not everybody was able to participate. So Francisco, if you can just share one slide and tell us in 1 minute the conclusions of your presentation. Francisco is coming to us.
Yes.
It's just that everybody sees what was your work.
Just a moment while Francisco is sharing his screen.
Yes, please, Marco.
The registration of this session will be available for all the attendants. So also the first 2 presentations that we had some problems, as you know, in our server, will be available for 1 year in our platform. So that's to be clear for, and also for respect to the first speakers.
Okay, thank you very much, Marco, for this explanation. So Francisco, takeaways, please, so everybody is on the same level here.
Yes, so the takeaways from my presentation were that if you have a really good understanding of the distribution of our contamination, you can more effectively remove the meth. And in some cases, as the study case showed, most intrusive method might be considered sustainable if you consider the entire project life cycle. So the sustainable approaches and metrics, guides, and analysis should also take in consideration the whole project and not only specific parts, and therefore have the focus that the mass is the problem, and it should be a key point for the solution and their evaluation.
Okay, thank you very much, crystal clear. As you see, the presentation will be also online for those who want to see it after this teaser. And I would also ask the same, Sylvia, if you can present one slide as
okay.
takeaways from your part.
Yes, maybe 2 slides because we have a part related to the benchmark study and another related to any rewind experience. If
you might keep to 1 minute, it will be perfect.
Okay. Let me know if you see the slide.
We see the full screen, yes.
Okay. The outcomes of the comparative study, the management of contaminated sites is addressed with a different approach and tools at international level. And this has an influence on the definition of the cleanup goal, on the technology selection, and therefore on cost and time of the remediation activities. In particular, in Italy, we have the most conservative approach than the other European and not European countries. And we don't have a procedure to implement sustainable remediation. And that means that also the time and the costs in Italy are higher than the other countries that we have studied and analyzed. But in any event, we are trying to include sustainability aspect in our activities, and we are developing several tools to evaluate the remediation strategy according to sustainability and circular economy criteria. Here we have the 3 main tools that we are developing: a tool to evaluate the remediation strategy, a tool to implement a simplified life cycle assessment for remediation technologies, and a procedure to implement the cost-benefit analysis for a very complex site and remediation strategy. Thanks.
Thank you very much, Sylvia. Now we can see if there are some questions or maybe interventions. Voter, have you identified some questions to the speakers in the chat, or maybe you have some?
Yeah, there's a question for Sylvia. You mentioned passive sampling for monitoring mobility in the soil, but what tools are suggested or available to analyze and manage the adsorbed phase?
Okay, we can have the total concentration of contaminants performing traditional characterization activities, traditional investigation. But if we want to determine the mobile fraction who could pose risk for receptor, and we now we have to perform a human health risk assessment and use constant to transform this total concentration in a mobile fraction. But using passive sampling, we can measure this mobile fraction directly, so we can obtain cleanup goal less conservative, and so maybe the remediation activity could be easier for considering also the technology that we have that can we use. Sometimes it's difficult to reach these cleanup goals because are calculating using the total concentration and not the mobile fraction.
And the question is, what kind of tools do you have to measure this mobile fraction?
For the mobile fraction, we use this passive sampling. This is a polyethylene film that we put in the soil, and in this way we can measure this mobile fraction after attending for the chemical balance between the different phases that we have in the soil, water, soil, and air. And so in this way, we can evaluate the leachate, the possible inhalation of these contaminants.
Thank you very much.
You're welcome.
And there's a question for Kevin. What was the mass balance of contamination in the source zones?
Yeah, thank you. I already, between the breaks, I already chat with Matteo. So his main question was if we just consider the concentration in the groundwater, and his question was also mainly due to concentration in soil, because of course the organic compounds can still absorb. First of all, we cannot really every year monitor the soil for contamination in this case, so we just consider groundwater. Of course you can do, but with a higher effort. But nevertheless, we monitor the groundwater concentration, and their chlorinated amines are highly water soluble. So then when we do see an increase in concentration, then we consider okay, there are some residual fraction. And anyway, a main advantage of the compound-specific stable isotope analysis, if there is a dilution or solution from denapple phases of chlorinated amines to the source zone, then we would see again a decrease in the isotope value, because then the primary product is solved in the water, and this will be a hint that maybe there are some residual fractions. But his main question was, so all the calculations was done on groundwater, on the concentration in the groundwater.
Okay, thank you. And help my memory, your receptor down gradient was the surface water?
The receptor, so the area that has to be attracted. Yeah, this is like, yeah. So,
yes, and did you measure, as in other investigations already a few years ago, it was shown that the last meter before, well, the sediment layer between the aquifer and the surface water, there's a huge biodegradation activity over there. Did you take that into account in your calculations?
This specific not, because that was really the concentration was too low to consider. So this was really we are now in a stage that it's kind of reaching this area that has to be protected, but still really in a low concentration, where we have also a limitation. So it's still below 10 microgram per liter, but we have to investigate how's the development of the whole plume, and therefore we investigate further upstream. So you're right. So there can be considered some higher degradation rate constants, and also as we show for the vinyl chloride, because when you're talking about river sediments, whatever, we did observe in the lab microcosms experiments that the aerobic vinyl chloride degradation is possible with the sediment and with this groundwater. That's why it was important to do it in a multiple line of evidence approach. Then we have now already known about the sites and all the fallbacks and what we can do.
Okay. Then Piotr, if we still have 1 minute left for a question or not, help my time.
Yes, I think we are running a bit out of time, but please, if you have a question, burning question.
Then there's a last one on the excellent presentation on contaminated sites in Republic of Serbia. Did you publish the results of this project?
Hi, yes, we did. All results of this project are shown and published within the publication towards soil decontamination in the Republic of Serbia, and I will provide the link. But I think that on the end of our presentation, there is a link of that publication. So all information about the project and the site investigation phase or site prioritization are within that publication. So I think that this is the end of our presentation. Yeah. Yes.
Yeah. Okay. So now it's clear that you are sitting in the same room, so that's okay.
Yes.
and we noticed as well that your contact details are on the presentation. So for the remainder of this question, I would suggest that you answer directly, or you communicate directly on the questions. Piotr, over to you.
Yeah. Thank you.
Thank you very much. We are a bit running out of time, so I think we should be closing this session. It was really interesting. I saw a couple of comments in the chat. I think that all the presentations were clear, and we have to congratulate all the speakers, because it was a really good job on different aspects of contaminated sites. As I told you at the beginning, we are looking at this more and more in details. We are looking for statistics, we are looking for methodologies on characterization, on prioritization, This is really a very important subject, especially in the Green Deal perspective and zero pollution ambition to manage by 2050. So let's make this link to the policy perspective. Thank you very much. Maybe I will leave the floor for Marco to make an advert of the next sessions still today, and also the rest of the program. Marco, please.
Thank you, Piotr. In this PC, I don't have the general timetable. I don't know if you have, Piotr, to share it, your screen. Basically, we have another two sessions. One is running, already running. I see on the other side because I have two rooms, one in front of the other, on PFAS, and it's organized by US Army Corps of Engineers. So if you want to stay these 25 minutes at least, they are already running. This, and you find in the chat a message from Patricia that sent you already the Zoom link. I have an information now. They say that the Remtech Matters platform is back to use. So it was a crash of the system and adjourning the system. Unbelievable that happens the first day that we work. But however, it's something that happens, and I apologize. Take my apologies, Silvia, and I don't know who was the first one, Francisco, there were few people starting. But however, the registration, as I told you, will be absolutely available to any of you. Who will instead would like to go in deep with waste tailings and mining sites? I don't know, maybe there are also some experts. Wouter, also you have worked in mining sites sometimes in your career, right?
Sometimes, but a long time ago.
No, a long time ago. So take the opportunity to join session 4 that will start at least in 24 minutes. And so you copy the link that Patricia has posted into the chat in a way that you will be able to join. I would like to thank Wouter and Piotr for chairing this problematic session, but at the end it was really successful and really interesting. And what to say? Thank you, and see you soon.
Thank you very much, Marco, and to Wouter for co-chairing, and all the presenters who presented very well. Thanks, and see you in other sessions. Ciao, ciao.
Thank you. Bye.
Thank you. See you soon.
Bye.
Bye-bye.
Thank you. Bye-bye.
Thank you.
Piotr, one moment. You have to put stop the webinar. The way that everything will go, will stop the registration and everything.
I can stop the recording.
You may stop the recording, but stop the webinar also. Finish the webinar. There should be some button.
I have just the end.